Can you guys do question 1, please? Your Honor. You will need the election notes to do all the. You will need, and you got copies of the notes with you. If you don't have a copy, I have a spare one. You guys have a copy of the election notes with you. I have a spare one if you want. You can borrow this for £10 if you want. Anybody who hasn't got this? Did you have this one?
I can get it.
Okay. Yeah. What about you, sir?
I'll just go.
Okay. You have this? You can borrow this for a while. Because you need the notes to do question all the time. Sorry, the whole question.
That's stuff on integration.
They should have to integrate the PDF to file.
Yeah, show it to me later. Let me, okay, yeah, show it to me.
I'll just show you two later.
Alright, you guys done question 1. I mean, it's pretty, all you need to realize is that you just need to use the nodes, guys. So you have, alright, this is question 1. Shade 9, okay? And so you asked to find the power function of theta, because theta is the parameter, right, which is as you know, the definition of power function is the probability of rejecting given the value for theta. Now for this hypothesis, guys, what is the rule for rejecting null hypothesis? If you look at the nodes, guys, if you look at the lecture notes, you will see I'm sure you guys have the notes with you, right? Yeah. election odds, guys. You will see that for the given hypothesis, the rule for rejecting the null hypothesis is root of n divided by sigma do you guys see this? Do you see this, guys? Do you know where this comes from, guys? No? Yes? You have to look in the notes, guys, because look, we are trying to test the hypothesis here, theta equal to theta 0 versus theta less than theta 0. The corresponding rejection rule is this one. It's in the lecture notes on page, I can't remember the page number now. I think it's page 21. Is that right? Yeah, page 21. See, for all men, I don't have a good memory, but right now, to work this out, guys, what you must realize is that the true population mean is equal to theta, not theta 0. So the first thing you must do is to replace theta 0 by theta. So that means you need to add a theta 2. Now the next step is to take this guy to the right hand side. Okay, I mean, I've done this several times, so you should be kind of bored by now by this. Okay, now if you look at these guys, what can you say about the distribution of this? You probably should go back to week 1 or week 2. You will remember that one of the results I proved in week 1 or 2 is that the x bar, the sample mean, has a normal distribution with parameters do you guys remember this? I proved this in week 1 or 2, I think. Now if you use this result, right, then this will have the standard normal distribution, right? So this is equal to the probability that NO1 is less than minus yeah, yes. Now, remember here I have dropped the conditioning has been dropped when you come to this step, because I have used the conditioning that the true population mean is theta to argue that this has a standard normal, and therefore we have used the conditioning. Therefore we don't need the conditioning anymore, right? All right. So the final step is you can write this as phi or phi . Yeah, so this is the power function of theta for question 1. Are you okay with this, guys, or not? Yeah. All right. Let me also do question 2 because it's similar. It's very similar. So let me do question 2 too. Okay. For question 2, the only difference, guys, is that instead of being less than, you just have greater than, right? So the pi of theta is simply the probability that root of n by sigma x bar minus theta 0 is greater than z of a given theta. Okay. So once again, I do the same thing as before. So I replace theta 0 by theta, so I need to add a theta. Okay. And the next step, as before, is to take these two to the right hand side. So you'll get the probability that root of n by sigma right now, condition on the fact that the true population mean is theta, this guy here must have the standard normal distribution, right? Therefore, this is the probability that n normal variable, a standard normal variable, okay, and this you can write as 1 minus phi at z alpha okay. So this is the power function for question 2. So it's very similar to question 1. The only difference is you have greater than instead of being less than. Right? And you guys, is that okay, guys? All of you? And is that okay, all of you? If this is okay, can you do question 3, please? Oh, you should go. You follow that, right? Okay. Beautiful. You guys do 3 and 4, please. So question 3, question 4 are all similar. Once again, you need to use the lecture notes. If you don't have it, let me know. I can please. guys done question 3 yet? Alright guys, so let's see how we can do, if you haven't done it. I mean, I know many of you have already done question 3. So let's see how we can do so here the power function is a function of the parameter p. P is the proportion, right? So once again, by definition is right. So this now for the given hypothesis, if you look at this in the lecture notes or the scan notes, you will see for this hypothesis the rule for rejecting. I know I gave 2 different rules because one was the one in the printed notes, then I gave an alternative rule, but I would use the one in the printed notes, right, which says that you will reject the null hypothesis. Correct me if I'm wrong, because I'm just writing this from my own memory. Is this right, or is this correct? Yeah. Okay. So this is the version in the printed notes, although I gave another version in the scan notes also, but I would prefer if you use this one. Right. Now the true proportion is p, not p0. So the first thing you must do is to replace the p0 by the true proportion, which is p. So you need to add up p and do this. Alright. The second thing is to, as before, take these 2 terms to the right hand side. So this will become right. And the next thing is I'm going to use an to argue that this has a standard normal distribution. I'm going to use an approximation. This is not an exact result. I think I mentioned this before in the class anyway. So this is not an exact result, but it's an approximation. Right. So I'm going to use this approximation to argue that this has a standard normal distribution. So that means approximately equal to the probability that a standard normal variable is less than yeah. Right. So you see I have used an approximation here, not equal, not the equal sign. Right. And once again the conditioning on p is no longer needed because we have used the conditioning to argue that this is approximately normal, right? Now this you can write as phi Alright, so this completes question 3. Question 4 is very similar, so I might as well do it now. So for question 4, sheet 9, the only difference is that in place of less than you have greater than sign. Okay, so everything is pretty much the same. Okay, so you have the probability that yeah, so this is the rule for rejecting for question 4, and once again you replace P0 by P because the true proportion is P, not P0. Okay, and the next step is to take these two guys to the right hand side, so to become sorry. To become this. And the next step is, as before, using this approximation one more time, we can argue that this is approximately equal to the probability that a standard normal variable is greater than right, and the final step, I mean, you can leave it like this if you wish, but it'd be better to write it in terms of phi. The phi is the standard normal CDF. So this is 1 minus phi at Z alpha. All right. So this is the power function for question 4. The reason I have finished the 4 questions so fast is because you may remember last week in the example class we did not complete all the questions. I'm just trying to find out the sheet here, but I can't find it. Does anybody has a copy of sheet that we did last week? Do you guys have a copy of the sheet 1? I think it was sheet 5 we did last week. You have it? Okay, thank you. Thanks so much. I'll just borrow it for a sec. I'll give it back to you. If I forget, let me know. Right. You probably remember this. Anyway, by the way, are you guys clear with this or not? Are you alright with this, guys? Yeah. All right. Now this is sheet 5. This is the sheet that we did last week, right? You remember this, guys? Yeah. Yeah. But we did not complete all the questions. I think, if I remember correctly, we did only question 1 to 4. And we did not do question 5 or question 6. So what I'm going to do is I'm going to do question 5 and 6 today. Okay. All right. So the first thing I want to do is question 5. So this is. Let me keep it. I'll give it back to you in a few minutes. So the first thing I want to do, guys, is question 5 of sheet 5, right? The question goes like this. It says that you have a sample, a random sample from a normal distribution with parameters mu and 20. And you're testing the hypothesis that mu equal to 100 versus mu less than 100. And you're told that alpha is 0.05. Remember, alpha is the probability of type 1 error. And the question is, what is the value for n so that the probability of rejecting H0, given that the true value of mu is 95, is greater than 0.9. So that's the question. The question, and you probably remember vaguely from last week, right? The question is to find the value for the n is the sample size, such that the probability of rejecting the null hypothesis when the true value of mu is 95 is at least 0.9. Okay? And maybe some of you already did this question. Anyway, if you haven't done it last week, let me show you how to do it. Now, for this hypothesis, the rejection rule, once again, if you look in the lecture notes, guys, you will see that the rejection rule for this is root of n divided by sigma, which is root of 20, times x bar minus mu 0, which is 100, less than minus do you see where this comes from, guys? Yeah, do you see where I got this from? It's from the lecture notes, the rule for rejecting the null hypothesis. Yeah. Now we are conditioning on the fact that the true mu is 95, not 100. So the next thing we must do is to change this to 95. Okay, so I'm going to change 100 to 95, right? That means I need to add a 95 and keep the 100. Alright, the next thing, I'm going to group these two guys and take them to the right hand side. It's the same as before. You must be kind of bored by now. 95 minus 100 is minus 5. So if you take minus 5 to the right hand side, it will become a plus 5. So it will be 5 root of n divided by root of 20. Okay. Now, this guy here, this guy here must have the standard normal distribution because the true value for mu is 95, right? So what you have here, guys, is that the probability that a standard normal variable is greater than yes. So this is, what did I do? Sorry guys, you should be less, you must have, stupid of me to do this. This is less than, right? All of a sudden, you must have mentioned this. This is all less than, not greater than. Less here, okay? Did you notice that? I'm sure some of you noticed this. Yeah. Alright, so what you have is phi or phi yeah. Now the thing is, what we need to solve this inequality for n. So what's the next thing we should do, guys? We want to solve this. What you have here is an inequality, and we want to solve for n. So the first thing you must do, guys, is to multiply both sides by the inverse of the function phi or phi. So if you multiply the left and the right by that, you get you see what I'm doing? You see what I've done? I have multiplied both sides by the inverse of phi function. So you get this. Okay? Then take this to the right hand side. It becomes 5 root of n divided by root of 20 is greater than this. Yes? And then take these two to the, this becomes root of n greater than root of 20 divided by 5 in brackets. Yeah. Now finally, if you square both sides, this will become n greater than 20. Square of 5 is 25. So this is the answer, guys. Do you guys follow what I've done? So the answer to the question is that the sample size must be greater than this number. Of course, if you have a calculator and a table, you can work out what that is, right? I'll let you do that by yourself, right? This is kind of clear, guys. So it's kind of working backwards to find the sample size. It's the same. The procedure is pretty much the same for every question, but sometimes you are given the value for n, and sometimes you are asked to find the value for n. Right? In this case, this one is the latter case, right? Okay. Are you clear with this? Yeah. You right, guys? Yeah. Okay. All right. Now, let me do. So that was question 5 from last week. Yeah. You guys okay? Yeah. Question 6. I also did not do question 6 last week because we ran out of time. So this is do you guys remember this question from last week? Question 6. Now let me show you how to do question 6, okay? So this is yeah. So here, you should read the question, guys. You probably remember. You have right. So you are given the hypothesis that sigma is the population standard deviation equal to this versus this, And the sample size you're given is it 34 or 35, I think. It's 35, right? Sorry guys, I think it's 35. Sorry guys, because I don't have my glasses with me. I think yeah, it's 35. Sorry, it's 35. Yeah, the sample size is 35. Alpha, the type 1 error is 0.05, and you're asked to find the type 2 error, probability of type 2 error. Remember, the type 2 error is defined as the probability that you accept null hypothesis given that H1 is true. Now, in this case, you can write this as 1 minus the probability, well, in general, you can write this as 1 minus the probability that you reject H0 given that H1 is true. In this case, H1 is true when if sigma is, you're told that the true value of sigma is 2 times 10 to the power minus 2, which incidentally satisfies the alternative hypothesis H1, right? Because this is greater than this, yeah. Now, can you tell me, once again, look at the lecture notes, what is the rule for rejecting the null hypothesis in this case? This is once again in the lecture notes, guys. It says what? It says 35 minus 1 times s squared divided by sigma 0 squared, which is this, greater than chi squared 35 minus 1 alpha is 0.05. Guys, do you see where this comes from? Yeah. This comes from the lecture notes. I can't remember the page number now, but if you look at the right place, you will see this. Yes. So what you have is 1 minus the probability that 34 times s squared divided by 10 to the power minus 4 is greater than yeah. Now you must realize that the true value of sigma is 2 times 10 to the power minus 2. So the true variance will be what? If this is the true value of sigma, then the true variance would be will be 4 times. You follow what I'm saying? If this is the true sigma, then the true variance will be 4 times 10 to the power minus 4. So because I have introduced the 4 here, I need to multiply by 4 too. Yeah. Right, the next step is I'm going to take the 4 here to the right hand side, so it will become 1 divided by 4 times this given this. Now let me ask you a simple question now. What can you say about the distribution of this and why? This is stuff we did in the notes some time ago. This is in the lecture notes, guys. What is the distribution of this and why? Hmm? 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 Come on, guys. We did this several times. I applied this recipe several times in the lectures and also in the exam classes. Huh? Chi squared, yeah. And why is that, guys? Because if you look at, right, this is where the nodes comes in, guys. If you look at equation 72 on page 16, if you look at equation 72, it says that n minus 1 times s squared divided by the true variance has a chi-square distribution with n minus 1 degree of freedom. Yeah. Okay. So this guy here follows a chi-square distribution with 34 degrees of freedom, right? Now we don't need the conditioning here anymore because we have used the conditioning to argue that this has the chi-square distribution, right? And finally, this you can simplify to right, guys. So that this is clear to all of you guys. I mean, you need to realize. Thanks so much. You need to realize which property to use and when. Yeah, so is that clear? Everybody sign the definition, guys. Yeah, it doesn't matter because we are assuming x bar is the same as normal, which is a continuous distribution. So if less than is the same as less than equal to, and greater than is the same as greater than or equal to. So because we are assuming that x bar is normal distribution, which is a continuous distribution. So it does, yeah. Yes, it should be minus here. It should be minus here. Did I not put a minus? I think maybe I forgot. It should be a minus here, yeah. It should be a minus. Sorry. Oh, you want to ask a question? Do you know what's been done here? Yeah. Okay. Is it Zach here?
Yes, that.
Can I just what you do is I'll just give you a hint, okay? I'm not going to do the whole thing for you. What you do, you write that as that minus a plus a, and then that minus a plus a minus a. That's what I've done here. Yeah. Then you group these two. Okay. Then it will become, you have variables, right? Because you have this v of the function, which is that minus a, and is that, and you have n times a of v minus a, is equal to these two cannot fit together. I mean, you should know how to integrate these. Yeah. That's a trick, man. It's just a trick. Otherwise, it's difficult to integrate. That's a trick. You need to learn this. Okay. Good. Question one. Okay, you want to copy? I will put it later online, but you can copy now. Yeah, this is question. This is question 1, question 2. Yeah, okay. You can sit and do it. Range. Did I send you an email? I think I sent you an email with the range. I can send it to you again. Just write your name here. Can you write your full name? I'll send it. It's only the first 4 weeks. I think it's only up to Emily. Only up to Emily. We need. I will send it to you again just today. You guys all signed the apprenticeship, guys. You haven't. You work it out and you still have problems with contact I'll have a good Easter break. So, yeah. Have a good Easter, man. Have a good Easter. Yeah. Yeah, thank you. Bye.
I saw you improve one example using the beta distribution.
Yeah.
And I think it was too complicated. So do I remember that all
You mean yesterday?
formulas?
In the class yesterday?
Yeah. The PDF of beta distribution.
It will not come in the test because it may come in the exam, but not in the test now. Let me show you. It's this one, yeah.
I think the beta distribution and the gamma distribution.
Yeah.
The formula is too complicated. Should I remember?
They will not come in the test, but they may come in the exam though. But they're not really complicated, man. You just need to remember them.
Okay.
Yeah, they're not really complicated. Now, like this, like you have a gamma function here, and then you have a product of two gamma functions, and then this and this. That's it. It's not really difficult.
Okay.
What do you think is complicated?
And I went to your office yesterday in the afternoon, but you were not here. You are not there.
Yesterday?
Yeah, like 5:30 p.m.
5:30. I'm only here from 11 to 5.
Oh.
Not after 5. I'm not here.
Okay.
Do you want to see me now?
No.
You can come now if you want. You're free now.
I have class, and I just want to ask some question about the undergraduate project.
Project. You want to do a project with me?
Yeah.
Yeah.
Because
Yeah.
I never do that before, so
Yeah.
I want to know about it.
Yeah. Okay. You can come and see me.
Do you?
What about 4 o'clock today? 4 p.m. today.
I've got until 5 today, in the
5
whole
today.
afternoon. Yeah. So are you and were you in the Anton building in the Easter holiday?
No, not next week. Next week I'm going. I will not be here. But the last 2 weeks of the Easter break I will be here.
Oh.
But I can send you some information by email. You send me the email. Where is it? You wrote your email down here.
Yeah.
Yeah. Where is it? I'm trying to find out where.
And if I want to do your project, should I?
Sorry, write it again. Write your email. Sorry, your full name. Yeah, write your full name again. I will send you details about the project by email.
And if I want to do your project, should I register during the Easter holiday.
Yeah, yeah, you need to fill in a form, I think. You need to fill in a form and just put my name and your name
Yeah.
and the title of the project.
And it always finished by myself. Not a group.
No, not work, no.
It's like some essay.
Yeah, writing an essay.
Okay. Exactly.
Good. Yeah, I'm happy